In the previous video, we talked about tangential acceleration. Now, the interpretation of tangential acceleration is that it tells you how an object's speed changes as it goes around a curved or circular path. Now, a change of direction also constitutes an acceleration. So if you want to account for the acceleration due to a change in direction, that's known as centripetal acceleration for circular motion. A centripetal acceleration points toward the center of the circular path that you're traveling on. So for instance, let's consider a car that's driving around a circular path. So we're looking top down on this car. It's going around the circle at a constant speed, but its velocity changes, even though its speed is constant, because its direction changes. Its initial direction is this way, pointing straight to the right, and then at some later time, its direction has changed. It's making an angle now. So if I just draw these two velocity vectors, v1 and v2, and find the difference between them, delta v, I notice that that difference vector points toward the center of the circle. In other words, this difference in velocity is centripetal. It points toward the center of a circle. Now, acceleration is defined as delta v over delta t, which means that the acceleration of this car also points toward the center, because acceleration vector has to point in the same direction as delta v vector. So that acceleration vector is centripetal. It points toward the center of the circle for the circular motion. And you can show that it has a magnitude equal to the speed squared divided by the radius of the circular path, which is also equal to r omega squared over r, or r omega squared. So the magnitude of that centripetal acceleration, AC, equals v squared over r. That's a pretty common equation that we're going to be using quite a bit. So just to sum up these ideas once more, when you have an object that's traveling in a circular path, or you're looking at a point on a rigid object that's moving in a circular path, there is tangential velocity that's tangent to the circle. There is tangential acceleration that's telling you how the speed changes, whether it's speeding up or slowing down or staying at a constant speed going around that circular path. And there's centripetal acceleration that tells you that the direction is changing. So it's always the case for circular motion that there's centripetal acceleration. If you're moving in a circle, by definition, your direction is changing. You don't always have tangential acceleration. It's possible to travel in a circular path at a constant speed, and in that case, there's zero tangential acceleration. By the way, our textbook uses AC for centripetal acceleration. Some people also use AR. That's another symbol that means the same thing. It's R for radial, pointing in the radial direction, meaning toward the center of the circle. I tend to use this notation a little more. I'll try to remember to write AC like our textbook does, but sometimes I forget and I write AR instead. Just keep in mind they mean the exact same thing. Okay, let's look at example 7.5. Let's consider a race car, maybe this car that's driving around a circular track of radius 400 meters. And that race car accelerates from an initial speed of 40 meters per second to a final speed of 60 meters per second. It takes 5 seconds to accomplish that acceleration. So here are a few questions we can ask. Part A. What is the centripetal acceleration when the car reaches a speed of 50 meters per second? So when the car is kind of halfway through this acceleration process, what's the centripetal acceleration? Well, that's pretty straightforward. We just plug into the equation we just learned. AC is v squared over r. V is 50 meters per second. R is 400 meters. 6.25 meters per second squared. What's the angular speed at this time, or angular velocity at this time? What's angular speed when v is 50 meters per second? Well, we have a relationship that we learned earlier between angular speed and tangential speed, or tangential velocity, v over r. So 50 meters per second divided by 400 meters, and that gives you 0.125 radians per second. And like I was mentioning in the last video, these radians can disappear or they can appear when we need them to. In this equation, v is meters per second, r is meters. There's no radians here, and yet over here suddenly there's radians. This is just to remind ourselves that we're talking about a measure of angle. It's not saying that radians really have a physical dimension to them. It's just kind of a reminder that we're dealing with angular motion. Question C, what's the tangential acceleration? So we'll look at this whole speeding up process from 40 to 60 meters per second. The tangential acceleration is just our regular understanding of acceleration. It's the linear acceleration. So it's 60 meters per second minus 40 meters per second over 5 seconds, which is 4 meters per second squared. So tangential acceleration is just telling you the rate at which the car is speeding up or slowing down. Now question D, what's the total acceleration? Well, when we say total acceleration, we're thinking of acceleration as a vector with two components, and instead of imagining an XY coordinate system, we're now imagining a polar coordinate system with a tangential coordinate and a radial coordinate. So acceleration vector is really tangential component and radial said I wouldn't write that. I said I would use C, the centripetal component, which means that the magnitude of the acceleration vector is given by the Pythagorean theorem. It's the same thing we did with our x, y components for other types of vectors. Now we're just saying instead of x and y, we have tangential and centripetal. So just plug in the values that we calculated here. We've got 4 meters per second squared for tangential. We have 6.25 meters per second, 6.25 meters per second squared for centripetal, and that gives you 7.42 meters per second squared.